The evolution of microchips is astounding. Technology has increased through the years so much that we can't even keep up. Most people do not know where the name derived from, but we will cover this today. Microchips are everywhere. With the advent of amazing technology comes a greater need for efficient microchips. But they sound minuscule, so if you're wondering about how they are made, we'll discuss that in our video. Welcome back to Technology Yap, and today we'll be talking all about microchips. But before we delve into the world of manufacturing, make sure to click the subscribe button if you haven't already. What is a microchip? Microchips are a flat silicon disk that has an integrated circuit embedded on it and even incorporates transistors. There are patterns of tiny switches that are created on the silicon wafer by embedding materials to form a deep and integrated lattice of interconnected shapes. There are elaborate processes that lead to the construction of these interconnected circuits, and we'll discuss all of them in detail. Raw material silicon is digital gold in the technology industry, as it is a widely used semiconductor. The manufacturers often improve the properties of the semiconductor by adding phosphorus or boron. The great news is silicon is made from sand, which is the second most popularly found element after oxygen silica. Sand is a form of silicon dioxide from which silicon wafers are made. The first step for this is by melting the sand into a shape of a large cylinder called an ingot, from where the thin wafers are sliced off. For microchips, good and pure silicon is always a mandatory material. Hence, only one impurity atom for every 10 million silicon atoms is allowed. Silicon balls are made in a range of different diameters, where the most common sizes are 100, 50, 200, and 300 millimeter wafers. Now for microchips, the silicon wafers must be really thin. Hence, there is a special sign technique where these wafers are made. Why is silicon used? Silicon is a semiconductor that is an efficient conductor of electricity, provided certain conditions are fulfilled. Every silicon atom has 4 outermost electrons, because of which actual pure monocrystalline silicon is non-conductive at room temperature. To make it conductive, small quantities of specific atoms are to be added as impurities to the wafer. This process is called doping, and most often boron and phosphorus atoms are highly used. The most suitable elements in these groups are very close to silicon on the periodic table and thus have very similar properties. The p and n conductive layers are very important, and the most important part of the chip is the transistors that are built on the p and n conductive layers. The wafer transistors are the smallest control units in microchips. Their job is to control electric voltages and currents. They are by far the most important component of electronic circuits, as every transistor on a chip contains p and n conductive layers. These layers are made of silicon crystals, and they also have an additional layer of silicon oxide, which acts as an insulator. A layer of electrically conductive polysilicon is coated on top of this. Step 1. Layout and design. Microchips have to always be carefully designed, as these are highly complex chips that are made up of billions of integrated and connected transistors that make up complex circuits, such as microcontrollers and crypto chips. A few square millimeters have to be measured in size and carefully outlined. The actual number of microcomponents requires an in-depth design process that defines the chip's functions. This actually characterizes the chip's technical and physical properties. In fact, special design tools are used to draw up the plans for integrated circuits and construct a three-dimensional architecture of sandwich layers. This blueprint is transferred to photomasks to give the geometric images of the circuits. The photomasks are used as image templates during the subsequent chip fabrication process to make sure that the microscopic structures of a chip are reproduced perfectly. These are the patterns that you've seen on the microchip. They have to be made in a dust-free environment with stable temperature and humidity levels. Step 2. Putting it together in a clean room. The chips have to be made in a clean room where no more than 1 particle of dust larger than 0.5 centimeters is allowed in around 10 liters of air. This place is extremely sophisticated, with several million cubic meters of air being circulated every hour and hundreds of air volume regulators maintaining a constant airflow. The employees in these production areas have an extremely strict dress code. It is here that all the airlock chips are built on a base wafer that is cut from a silicon ingot. Depending on their size, several dozen or several thousand chips can be made on one wafer. Because of their small size, the surface of the wafer is oxidized in a high-temperature furnace at approximately 1000 degrees Celsius to create a non-conductive layer. After this, a photoresist material is uniformly distributed on this non-conductive layer. Then, centrifugal force is used on this coating, and the process creates a light-sensitive layer. The wafer is then exposed to light through the photomask and special exposure machines called steppers. Here, coaster-sized areas of the chip are used to transfer the complex geometric patterns of the circuit design to the silicon wafer. The exposed area of the chip pattern is developed, revealing a layer of oxide below. The unexposed part remains as it protects the layer of oxide. After this, the exposed layer of oxide is etched off in the areas that have been developed with plasma etching. In this process, special gas is bonded with a substrate to be removed in the reaction chamber. This enables the microscopic layers to be removed in the windows that were exposed and developed in the previous step. Once the photoresist residue has been stripped, and after the wafer has been cleaned, it undergoes further oxidation. The polysilicon is then deposited on this insulation layer, and then the photoresist is applied once again and the wafer is exposed to light through the mask. The exposed photoresist is stripped again, and now the polysilicon and the thin oxide layer is etched off these two layers. Step 3 doping process. This is the process where impure atoms are introduced into the exposed silicon, and the ion implanter is used to include impurity-inducing atoms into the silicon. This changes the conductivity of the exposed silicon by mere fractions of a micrometer. After the photoresisting residue has been stripped, another oxide layer is applied and the wafer undergoes another cycle of applying photoresist exposure through the mask. The stripping contact holes are etched to allow the conductive layers, enabling the contacts and interconnections to be integrated into the wafer. This is done by depositing various metal alloys onto the wafer in a specialized machine. This increases the efficiency of the microchips. Step 4 smooth finishing. The photoresistant masks are applied such that the unexposed strips remain, as is after the etching process. This provides a point of contact to the underlying layers to give the insulation layer a smooth finish. This requires a chemical-mechanical process, which is used to polish away excess material with micrometer accuracy. These individual steps may be done many times in the fabrication process until the integrated circuit is finally complete. Depending on the size and type of the chip, the wafer will now have several dozen to thousands of chips. The individual chips are usually sought out of the wafer, and the chips are not lined up flush with each other on the wafer. This is because the tiny parts of the wafer splinter off during the sewing process. Hence, a certain amount of space, known as the scribe line, is always kept between the individual chips. There are structures also put in this scribe line to take the measurements immediately after production. This is to just find out if the chips are of sound quality. These specific structures are destroyed later during the sewing process, and the size of the resulting chips typically varies between 1 millimeter and a few square centimeters. Step 5. The assembly. The assembly is the stage where individual chips are placed on a package and the terminals are connected. The result is a thinner semiconductor device that can be mounted on circuit boards, employing the various types of terminals over many connections. There also would be ready-made semiconductor components and larger packages that are used for power-related activities. The semiconductors are made for many applications, such as trains, electric cars, solar panels, and wind turbines. Tell us your thoughts about how microchips are made. We want to know what you think about the process. In the meantime, don't forget to like and subscribe for more exciting content. See you in the next video.